Well, welcome to a snowy Friday afternoon. I have been out snow blowing, shoveling, and then again, just to get the dogs out. So I hope that you're all in a safe, warm place. This afternoon, I'm going to just take some example quiz questions from our thermodynamics chapter and kind of work through them and see if that will jog any questions. Feel free to turn your microphone on at any time. And also use the chat if you'd rather do that. So welcome. Let's go ahead and get started. So I put a slide together to remind us that our topic is thermodynamics, and I wanted to make sure that you have in your head a good working knowledge of that vocabulary. There are test questions that will ask you specifically, what does the first law of thermodynamics say, or what does the second law or third law respectively? And so I just pulled this from, well, two sources. One of them is from our note pack, and the second is just from your textbook. So these are like classic definitions that you're probably familiar with just from having to write them down. First law of thermodynamics was actually last module, looking at energy cannot be created nor destroyed. It sounds an awful lot like the law of conservation of mass, doesn't it? Where we say matter cannot be created nor destroyed, just converted from one form to another. And I know that we talk about converting one type of energy into another, kinetic into potential, or chemical energy into mechanical energy, and so forth. So that all kind of wraps up first law. Then in our new section here in Module 2, we introduced this term called entropy, the random chaotic disorder of a system. And we know in nature, things tend to become more disorganized, that it actually takes energy to organize a system. So the spontaneous direction is more chaotic, more micro states was that definition. And so just thinking about the second law, the entropy of any isolated system always increases. So if you're asked in kind of the multiple choice format to grab the second law, look at entropy increasing as time goes by. That's the natural state. Things become more disorganized. And then the third law of thermodynamics, this one represents how the thermodynamics data gets presented for entropy. You know, the Appendix C from my notes when I gave you a link to pull up all thermodynamic data. And in ALEX, it had a nice link that you would just click and it would bring up thermodynamic data. Well, that chart for entropy is based upon the third law of thermodynamics that says, as you approach absolute zero, right? Nothing colder than absolute zero. Entropy also approaches zero, so that all molecular motion, all atomic motion actually stops. So the key here is the entropy of a pure crystalline substance at 0 Kelvin is zero. And of course, we never run reactions at absolute zero. So as you begin to warm the system, the molecules gain energy and the entropy then becomes more chaotic. So entropy always has a positive value. So I just wanted to kind of touch on those terms, make sure in your mind you can pick out, and again, it's multiple choice. So you just have to bring your eyes, okay, are we describing the first law, second law, or third law, in case you get some of those definition type questions. Now to kind of expand on that, I pulled this question from the multiple choice section. Okay, so again, this is just me pulling out example quiz questions. And I pulled this one just to highlight right after that third law of thermodynamics. It says, at 298.15 Kelvin, so you know that this is just standard temperature, we know that, all of the following except have a zero standard free energy formation. So all of the following substances have free energy, that's delta G, or it could be delta H. I just want to make sure we see that. It could also be delta H from like last chapter. We learned and I know I stressed in the last module's review session that any element in its natural state is assigned 0 for heat of formation. It's assigned 0 for Gibbs free energy. What's not true is that entropy is 0. That's not true, because at 25 Celsius or 298 Kelvin, everything has a positive entropy. Remember that third law said you have to be at absolute 0 to have 0 entropy, and that's not the case here. So entropy will always be a positive value for any element or any compound in those standard charts, because those are recorded at 25 Celsius. So with this question, really similar to the last unit that asked, what element is in its natural state and what element is not? So I went in and I pulled this periodic table. The one you see on the screen here is something I just Googled to add to this slide. It's not part of the question, but I wanted to remind you that you had a way, or, if it's been a long time since Gen Chem 1, or, it's a little rusty when you first learned about the elements, we're expected to know elements' natural state. In our last review session, I said a funny sentence: horses need oats for clear brown eyes. And I talked about that as those 7 elements being diatomic elements in nature. Ones that you see highlighted in yellow on this periodic table are gases at room temperature. There's only 2 liquid elements at room temperature, and clearly you see the vast majority of elements are solids at room temperature. So if you look at your choices, A says gaseous chlorine, B says solid sulfur, solid iodine, gaseous bromine, liquid mercury. Those are your 5 choices, and your job is to figure out which of the following substances has a standard free energy formation except. So we're looking for that rule. If I open that chat session, anyone brave enough to put in your guess and why? You can certainly open your mic and let me hear your thoughts. What would be the correct answer? Just guess.
Would it be D?
Excellent. And who spoke?
Oh, that was me, Ben.
Benjamin? Thanks, Ben.
Yeah.
Thank you. Yeah. So bravo. First of all, that's absolutely correct. And all of that long-winded talk I just went through, hopefully about the fact that we're learning that bromine is a liquid at room temperature. So when you see gaseous bromine, that adjective, that little state of matter, it doesn't match. So therefore, it would not have a 0 delta G. It would not have a 0 delta H. All of these have a value for entropy. All right, so that, those little tricky questions seem to be the ones that trip us up. And they think they look easy, but then sometimes they're the most missed question. But apply them from, logic of saying what element is not presented in its natural state, and your eyes drew right to that gaseous form of bromine. Perfect, because now we know it's a liquid. Beautiful. Okay. Let's take a peek at something similar. Here we see, which of the following has the largest entropy? Let me to read through the list. We have liquid water, gaseous hydrogen sulfide, solid water, and liquid hydrogen sulfide. Well, what might be a good first step is eliminating some choices just based on their phase of matter. Which phase of matter has the highest entropy?
Gas has the highest entropy?
That's perfect. So you know what? Based on that, I can eliminate choice A. I can eliminate choice D, and I can eliminate choice E because they're in different phases, solids and liquids. Now I've narrowed my choice to steam, gaseous water, or hydrogen sulfide. Between these two, how could I determine the largest entropy? And this is a trend that you'll see in so many different questions that are asking the same thing. It goes back to when we learned this key principle. Entropy increases with increasing molar mass. The heavier the molecule, oops, I wrote molecule because I said it, the higher molar mass. There I go. The highest mass, heaviest molecule will have the greatest entropy. And the reason there is just the wiggling and waggling of those bonds increases with that heaviness of the atoms. So when I look at this, here we have a molar mass of 18 for water, and here we have a molar mass of 34 for hydrogen sulfide. I can narrow down the list real quick by eliminating liquids and solids. And from the remaining choices, I want to just pick the heaviest molecule. And that's all there is to this question. The greatest entropy is the heaviest molecule in the gaseous phase. And there, we focused there for letter C. And I know there's multiple questions like this. So, that's kind of like the strategy for this question. Even if you're given a different list of compounds, it's the same strategy. Before I move on, any questions about that? And chat or turn on your microphone, either way. Let me know how you're feeling. Okay. From that pause, here's something else that you kind of consider. Along the same strategy, I won't take long, but just kind of give you a second view of the same question. Here you have a series of molecules. They're all hydrocarbons, and they're all in the gas phase. So now I'm being asked, the entropy of gaseous, here's a bunch of hydrocarbons, is the largest. What strategy would you use to select the correct answer, since they're all gases? I need someone willing to type that into the chat. What strategy would you use to find the correct answer? You got it. Thank you. So yeah, I'm just looking for the heaviest molecule. The heaviest molecule, of course, is going to have the most atoms in it. Beautiful. So what's interesting is I kind of did statistics on quizzes so far, those who have taken a first or a second attempt, and those were the types of questions that were most missed so far. So that's why I started with those. We can turn now to some practice calculations. All right, and remember, you have a formula page I gave you for this particular chapter. I would think for me it would be easiest to have those printed if you want and have them on your desk. Just show them to the camera, but they are always provided in the quizzes themselves. As you know, sometimes you have to scroll through them to find all the questions. Whatever you find easiest, you're allowed to have those formula pages out and handy. Okay, so here we have a calculation. Calculate delta G for the reaction below at 25 Celsius. And again, they're always going to tell you that standard temperature just so that you know the thermodynamic chart, which were all recorded at that standard temp. We know that our formula would be delta G is equal to delta H minus T delta S. The only reason I selected this, and I know you did a boatload of these on Alex, is just to remind us, typically, delta G is going to be reported in a kJ. Delta H is also recorded in a kJ. The temperature needs to go in the Kelvin units, and entropy, because they're smaller numbers than the kilo unit really allows, just keep in mind that this typically is given in the joule per Kelvin mole. So this is just my friendly reminder to make sure that your units match before you start plug and chugging your answer. These aren't tough, but I only selected it as that reminder. Kelvin temperature. Make sure you have your joules converted to kJs. Do I hear a mic open? Question? Nope. All right, so what we would take then is negative 20 or 231.1, and that's kJs, minus, and then of course this goes in as a Kelvin, so 298.15, and then times negative 287.6, and then I just like to set that over 1,000. You don't have to. You can slide the decimal 3 spots to the left. But when I write this, it allows you to remember that little trick of making sure you're changing the joule to a kilojoule. I'm going to grab my calculator. Would you guys do the same and make sure I'm not making a mistake? I like to have a calculator buddy with me. I'm going to just plug out this equation and see if we get a common answer. Negative 231.1 minus parentheses 298.15 times negative 0.2876. And if someone would confirm that that's what they found, that would make me feel better. Cool. Thank you. Any questions before we head out to the next example? As I said, Alex, really, I think you did this one probably 15 out of the 25 assignment questions. Cool. All right, so I'm going to take a look at this question. It says we're asked to estimate the boiling point of ethanol given the following thermodynamic parameters. We have a delta H, a delta S, and a delta G, all given to us in a data table format. And again, let me emphasize as last test, when you need thermodynamic data, it's supplied for you right in the quiz question. You don't have to go to a chart and look it up. So it's right there for us. So when we think about what the system is that we're studying, the boiling point of ethanol. Well, ethanol, in terms of C2H5OH, in the liquid form, turning into C2H5OH in the gaseous form represents the boiling point. Except there's one key part of phase change. Phase changes, I don't care if it's melting, freezing, or boiling, condensing, phase changes are dynamic equilibrium. And that is so key to this problem. Let me get that written down. Because the system in dynamic equilibrium, we know that the delta G is 0, that the forward reaction and the reverse reaction are occurring at the same rate. So this quiz question could be tricky because you might be fooled into doing products minus reactants to try to find a delta G. Don't do that. For phase changes, delta G is 0. And if you remember, even when you did phase changes, when you learned about intermolecular attractions in Gen Chem 1, you know, let's say you're at -10 and you start warming up water and then it plateaus, and then you warm up the liquid and it plateaus, just to kind of go from solid to liquid is this plateau. We had the liquid to gaseous phase in this plateau. Those are in dynamic equilibrium. So there's no temperature change. What this now becomes is solving for the temperature when delta G is 0 at dynamic equilibrium. So the gaseous phase is the product. So let's solve for delta H, products minus reactants. Alrighty, so the gaseous phase, negative 235.3 minus the reactant, which is the liquid phase, negative 277.0. And the entropy, the gaseous phase of entropy is 282.7 minus the liquid phase of 160.7. And I'm going to need just a minute to hit those. Negative 235.3 minus negative 277. My screen reads positive 41.7. 282.7 minus 160.7. I'm going to just wait a moment and see if someone can verify. So I hate to make a mistake when I'm trying to do things quickly. When I get that common answer, just for the delta H, delta S. We're not done with it, but before I go on, I want to double check that I've calculated so far correctly. Okay, got a yes. Thank you. And if I do make a mistake, please don't hesitate and tell me I made a calculator error. It happens, as you well know. Okay, so here's what we know. We have delta G is equal to delta H minus T delta S. Delta G is 0 in a dynamic equilibrium. Delta H, which by the way, this makes complete sense, doesn't it? That it came out positive, an endothermic reaction, because it takes heat energy to force a liquid to turn to a gas. That's an input of energy. So that value being positive makes perfect sense, 41.7. And then we need T. This also makes sense that the entropy came out positive because a liquid turning to gas, a gaseous phase is more chaotic. So that's a favorable condition. And I know that I have to do 122 over 1,000 to turn that into kJ. So we're subtracting like units. Alrighty. So we want to pull out temperature. This is the temperature that would be called the boiling point. And here it's just math from there. So I'll bring negative 41.7 is equal to negative point negative 41.7 over negative 0.122 will be T. So when I hit this, I found a positive temperature, positive 341.8 Kelvin. Friends, don't forget that oftentimes they're asking you to find it in a Celsius. So just as a reminder, subtract your 273 to find your Celsius there, and 273.15 I just did, and that would be your Celsius degree. So what might be a question you had about this? If you had seen this on your test, tripping points someone would face. Just give you a minute to process and see if you have a question you want to bring up before we move on.
Well, I would say that a tripping point for me would be probably knowing to set up the reaction. We'll set up the equation, the balanced equation.
The very first thing I wrote here. Is
Yes.
that what you mean, Ashley? Ah, good.
Yes.
So when we see boiling point, think phase change. Excellent point. Any other comments? You'll all ace this one now, right? Move on. I have a next example. This one I pulled from these. It says, here's a set of thermodynamic data. All right, so I see that I have gaseous PCl3 and liquid PCl3, and it's telling me this question, or asking me this question. Vaporization of PCl3 liquid is, and then I have some choices. So first of all, I put this problem directly after the last one on purpose because it allows me to see yet another question that makes me realize they're talking about a phase change. When PCl3 liquid turns into PCl3 gas, that's a phase change. That's called vaporization of PCl3. And you now know too, this is kind of that equilibrium, isn't it? To turn it from liquid to gas is at the temperature would be called its boiling point. So instead of saying really and actually solving for the delta T, it's asking us more of a conceptual question. So here, let's take the delta H, and I'm going to take gaseous delta H, negative 288.7, minus the liquid, and I'm going to find the delta H of that reaction. So let's see, products minus reactants, negative 288.07 minus a negative 319.6. And I'm finding an endothermic value of 31.53 kJs. And if I do the same strategy, entropy, I'll take the gaseous value, 311.7, minus the liquid value, 217. That's 94.7. Okay. What's interesting to answer this question is I really don't care about the number so much. I want to care about the sign for delta H and the sign on delta S. We know that the sign on the entropy is increasing. That when liquid turns to gas, that's an increase in entropy. So that's what this little chart is giving us. Oh, by the way, that chart is not part of the quiz question. It's a visual aid I put on there, and it's one that I put into the feedback of every person's thermodynamics discussion post. It's critically important to be able to to use this chart. I don't want to say memorize, but it wouldn't hurt you to know this chart, because it lets you remember what temperatures or what conditions a reaction would be spontaneous. So if delta H is negative, that's exothermic. If delta H is positive, that's endothermic. If entropy is increasing, that's a favorable process. But if entropy is becoming more ordered, that's an unfavorable process. To answer this question, you just figure out the signs on the delta H and the sign on the delta S and see where you land in this grid. I have a positive delta H and a positive entropy. That puts me in this quadrant of this chart. This reaction is spontaneous at high temperature when T delta S is large. So based on that knowledge, take a minute and just look through your choices and see if you can pull one out. Which one is the best answer? Do you see it? Who's going to be brave and type it into the chat or open their microphone? No one. I'll leave it here then. I'm just saying, based on that chart, you should be able to pull out an answer. And there's only one correct answer based on saying it has to be a high temperature. You can toss out all the others. All righty.
Can you see the chat? Because I think some people were typing it in there.
Oh, they are? Oh, my goodness. Thank you for bringing that up because I thought I could see it. Let's see. Oh, you're right. I see it now. I didn't scroll down. Letter A. Thank you, sir. You're absolutely right. And what's interesting is, I mean, there were two choices that say high temperature, but I want us to even think about this as being non-mathematical. To go from a liquid to a gas, I know that's an endothermic process, and I know it's not spontaneous, you know, that you have to input energy to force that to occur. Beautiful answer. Here's another look. I won't spend as much time, but I wanted to put a next example, just because when you see this type of question, I want you to look for the compound. I was looking at the example, like PCl3. I want you to look at the overall feel or flavor of the question. Here you're given some thermodynamic data, and you're asked about the vaporization of a compound. Remember, the vaporization is liquid turning to gas. And if we approach this truly in a non-mathematical way, I know that a liquid turning to a gas has an increase in entropy. I don't even care about the number. And I know that when a liquid turns to the gas, it has to absorb heat to do so. It is an endothermic process. And remember, if a gas cooled to a liquid, it would release heat, but a liquid has to absorb heat to turn into a gas. So I don't even have to approach this mathematically. I know based on phase changes that I always end up on this quadrant up here. Pretty cool. Good work. That was a good thought question. This one looks kind of scary at first, but it's along the same lines. I'm trying to find questions that aren't just computational questions, but kind of thinkers as well. It says diluting concentrated sulfuric acid with water can be dangerous. The temperature of the solution increases rapidly. You know, those keywords just told you something, didn't they? If the temperature is increasing, is that endo or exothermic?
Endothermic.
Interesting, because it's the opposite of that. And I'm so glad you said that, because I'm going to try to figure out why we would think endo. And this really goes back to last chapter too, doesn't it? An exothermic process is heat releasing, that as the solution is forming, heat is being expelled from the system, and that's why the thermometer is going up. If the thermometer goes down, heat is going into the system. That's endothermic. So this is a really good question to review. The term exothermic is heat releasing, therefore it's warm to your touch, And that's why, I mean, that's why it says it's dangerous, is because it gives off so much heat you could burn yourself. And when that heat's released, that's what's detected on the thermometer. So thank you for saying that. It's actually an exothermic process, heat releasing. And now you know the sign on delta H to be heat releasing. We know that exothermic is a negative sign, right? Endo would be positive, exo is negative. Okay. Then what about entropy? If you're taking acid and diluting it, you stir to create this solution, is that becoming more organized or is it becoming more chaotic? What's the sign on delta S? You're right, Michael. Oh, beautiful. Thank you, both of you. I agree that it's becoming more chaotic. Therefore, exothermic is a favorable reaction. Positive entropy is a favorable reaction. We now know the sign on delta G, guaranteed. Remember, that's this right here. If we have positive entropy and negative enthalpy, we're in the first quadrant, this is always, always spontaneous. And so therefore we know delta G is negative. It is spontaneous reaction. And now it just becomes a matter of trying to find the correct multiple choice part to illustrate negative delta H, positive delta S, negative delta G. That's the only choice that puts all in the correct order. And yeah.
So I have a question.
Go for it.
So for this type of word problem, are we supposed to like break down the different like components like that's provided for us, like the key words within the problem to find the delta H, delta S, and delta G?
Yes, that is the best advice. Use a single word clue. And then really just think about, you're pouring water into sulfuric acid, diluting it, adding volume. Of course, that's not becoming more organized. The more volume of water, the more microstates there are, right? The more dissipation of energy. So that's a more chaotic system. But this one, it seems like this sometimes trips students in remembering if a solution is hot to your touch, it's heat releasing. So that's a good key term there to know that it was exothermic. Beautiful. And then if I could emphasize over and over, maybe to really know this chart, it's so helpful in predicting delta G signs. Any other comments? Okay, you just stop me if something pops to your mind. And I'm just kind of going through slides I have, so if something else you'd like to bring up, please don't hesitate. Let's see, here's a reaction. Given thermodynamic data, determine the temperature in Celsius in which the reaction is non-spontaneous. So I have a reaction given to me. And it looks like what we'll have to do, of course, is find delta H by doing products minus reactants. We'll have to find delta S using products minus reactants. And then once we have those, we'll plug in to this equation, solving for temperature. And what that temperature is equilibrium. So when I solve for the temperature, I'm going to put 0 in. So let's back up. We'll go step by step. Let's do delta H first. The NH4Cl is negative 314.4 minus the sum of the product. So let's grab NH3 plus the other reactant, HCl, 92.3. And this is going to come out to be kJs. And while I'm here, I'm just going to set up next subtraction. Here is NH4Cl is 94.6 minus the sum of the products, or the reactants, 192.5 and 186.69. All right, let me have just a moment to solve these. 314.4 minus the sum of negative 46.19 and negative 92.3. My delta H came out exothermic at 175.91. Alrighty, good. Let me do that with the S. Let me have a moment with my calculator. 94.6 minus 192.5 plus 186.69. Okay, so I have a delta H in a kilojoule, the delta S in a joule, and I'm trying to solve for temperature at which it will become non-spontaneous. The trick with this type of problem is to put delta G in at 0. And when you do that, you're finding the breaking point for the reaction that will favor forward or the reaction that will favor the reverse. The reverse reaction would be non-spontaneous. So put delta G in at 0 and let's solve for the temperature. We have negative 175.91 minus, looking for the temperature, delta S, negative 284.59. I'm going to set that over 1,000 just to remind myself why I'm doing that, to change the unit into a kJ. So then, positive 175.91 over negative 0.28459 is our temperature. Let's see if I did that right. This negative and this negative turn this into a positive. Anyone else catch that for me? Do you agree? Minus a minus is truly a plus. I knew that I'd screwed up somewhere because temperature's never negative like that. They just won't be. On the Kelvin scale, there are no negatives. So that's kind of how I caught myself, 0.28459. Let me just pause a moment and ask you to see if you got the same Kelvin temperature when you solved that algebra. I'm going to just pause for a moment and let someone else confirm I'm correct with the calculations. Cool, Andrew, thank you. So oftentimes, just to remind ourselves, check the units. One of the tricky things I know in the multiple choice is they'll ask for you to do that in a Celsius and then have the Kelvin answer as one of the choices, but with the Celsius unit on it. And they're just tricky that way. So just make sure that if you're asked for Celsius, let's deduct the 273.15 and we'll report it as 344.96. Let's just round, let's say it's 345 degrees Celsius. Now that's the temperature at which it would be in equilibrium, right? When delta T is 0. To be non-spontaneous, it has to be any number lower than that. And so when you're looking at your multiple choice, make sure I mean, this isn't asking you exactly for the temperature when it's at equilibrium, it's asking you when it's not going to be spontaneous. And so you have to look for a smaller temperature, right? The reaction is non-spontaneous at any temperature below this one. And that's how you'll find the correct answer there. Let me give you a moment to think and see if something pops to your mind for a question. My dog is at my feet snoring right now. Are we thumbs up good? Is everyone? I don't hear a microphone on. I don't see a chat, so we're good. All righty. Please don't hesitate to interrupt me. I'll just keep going then. Let's see what's next. Oh, I pulled out a problem where we can incorporate equilibrium, calculating the K constant into the delta G formula as well. So not that these are tricky, I'm just trying to find different samples of, different varieties of questions. This one asks, what's the equilibrium constant for the reaction below at 25 Celsius? They even give us the R constant from the ideal gas law. Our reaction has gaseous nitrogen monoxide plus oxygen, making 2 units of NO2. They give us the value of NO. They give us the value of NO2, and we're asked for the equilibrium constant. Well, to find the delta G of your reaction, remember that it's going to be the sum of the products minus reactants. And I know I emphasized this last chapter as well. It's really trying hard to make a sigma, and they just come out as squiggly E's. I apologize. We're given the value of NO2, so 2 times the value of NO2 minus, and here's the reactants, we have NO, which is positive 86.6, and then no data for oxygen. And it seems like it's still a tripping point for some people who get upset where there's not a third data point. But we don't need it, do we? We stress that right at the start of our review session. Any element in its natural state is assigned a 0 for heat of formation, as well as Gibbs free energy of formation. So oxygen, is just a 0. So it's another little sneaky way I could get that in for review. Delta G is 2 times 51.2 minus 86.6. And I'm going to pause just to see if anyone's willing to verify that matches their calculation. Oh, cool. Thank you. All right, well, so now we have the delta G. We know our formula is negative RT ln K. So a good reminder, delta G is in kilojoules, but R is in a joule. It's like entropy value comes in a joule. So it's negative R, but it's 8.314 over 1,000 kilojoules per Kelvin mole. And then the temperature, which is 25, which is 298.15 Kelvin. And then LNK. And we want to pull out equilibrium constant. So I'm going to start with this algebra journey going negative 70.8, and I'll divide that by negative 0.008314. And I'll divide out again by 298.15. Looking good so far. We want to get the K by itself. And so we know the opposite of the natural log is Euler's number. So it's E raised to the 28.56 will give us our equilibrium constant. So I'll just do second function of the natural log and then of answer. And I get 2.5, I'll round a little bit, 4 times 10 to the 12th power. Equilibrium constants have no unit. Our whole next chapter is devoted to equilibrium. So this will make, a good tie-in is coming in our next chapter. But it's the magnitude of the number that we're interested in for our equilibrium constant. It's a large number, meaning that the products are being favored. The forward reaction is being favored. The larger the number, the more push forward the reaction is showing. That just allowed me to tie in an equilibrium constant problem, delta G, reminding you to make sure the R constant is in the proper unit. You've got a Kelvin unit and pulling out K. I'll pause. Please let me know if you have a question. You guys are so quiet today. Either that's a really good sign that these seem easy or you're lost. We're good? All right. I really don't have very many other types of questions. This is a similar, this one gives me the equilibrium constant K and then asks me to solve for delta G. I'm, just in the interest of time, there's a few left. I'm going to open up and just ask you what topic remains that you wish I would talk about before we end our review session. Do you have any lingering questions that were not hit upon yet?
Yes, could we talk about the microstates?
Yeah, so that's a really good question. I'm going to tell you on the quiz or on the test that's from the test bank, there's not a calculation with microstates as there was on your Alex homework, but instead it's more conceptually tested upon looking at how entropy increases as a trend, like from phases of matter to increasing more mass. The number of microstates calculations is not on the test. I know that on the homework they gave you a like a little atom and it was in so many circles that it could move into and you had to find with Boltzmann's constant. With the equation page provided, any conceptual microstate question can be answered just by looking at a formula, but I purposefully did not put on a calculation. Does that help answer your question? Excuse me. Was that Ashley who asked that? I can't remember.
Yes, thank you. Sorry.
Okay, no worries. I just thought maybe I stumped you. But no, so that's one of the reasons I didn't even put one on this review because I didn't ask you to calculate. So yeah, you're good. And other topics that, even for Sunday's review, don't be afraid to email me if you have a question that I didn't get to today. As you're taking your quiz attempts in the next day or two and you run into a problem, I would welcome an opportunity to kind of prepare a Sunday review if you run into trouble. I think this chapter, to be brutally honest, you're going to do better because it's so much a repetition of the last chapter. Products minus reactants, plug and chug into an equation. My last piece of advice, I have a tickle. I'm so sorry. Don't forget that there are 5 distributed practice questions from the first module. So, and as the tests progress through the term, you're going to have a few questions integrated from previous modules. So it wouldn't hurt you to go back and look at your notes there there'll be 5 questions pulled from that previous test bank. So just a piece of advice there. So with that, I'll look forward to hearing from you over the next day or two. Oh, awesome. Yes.
I was wondering if we could do the calculating the delta G using Hess's law. Could we go over that?
So certainly, I don't know if I have one made. I didn't pull one, I suppose, just because that's really the same skill as Hess's law for H. I don't know how to make that any different than the lessons we reviewed for last term or last module. Do you have one, Ashley, that you have in mind, or?
No, I just wanted to know like how to
Okay.
like tell if it's spontaneous or non-spontaneous. That's all.
That is as easy as saying delta G has to be negative. That's spontaneous. And if it comes out to be positive, then it's non-spontaneous. It's that simple.
Okay.
Hess's law is performed the same way if you're using delta H or delta G. So in other words, if you flip the direction of a reaction, you flip the sign. If you distribute a coefficient through a reaction, you're going to do that same coefficient to the magnitude of delta G. So it's so much of the same lesson. The only little twist at the end would be if it's spontaneous, you look at the sign on the delta G. That's all there is to that part.
Okay, thank you.
Oh, you're very welcome. Make sure, though, if you find one when you're quizzing and you want me to talk about it Sunday, just shoot me that in. Any other last closing thoughts?
Did we go over the reaction quotient expressions?
Reaction quotient expressions.
Yes.
So I'm trying to think of a place where you were trying to decide for the equilibrium constant K. Is that where you're referring to?
No, I was actually referring to what we did in our note pack where we had to find the delta G under non-standard conditions. Well, I guess that's it. Yeah,
I
guess
see.
that's it.
Yeah, that's this formula. And so, yeah, this is called the Nernst equation. But let me pull up before I start going over something that you don't need yet, because this non-standard condition it's tossed forward quite a bit. It's so what you might be thinking of right now is how we took a balanced equation and wrote out reactants over products and talked about equilibrium constants, and where the stoichiometry became the power with which you raise those molarities. But I have to tell you, I want to hold off on that a little bit because our entire next module is devoted to equilibrium, and all I was doing there was kind of sprinkling in lessons that are coming forward. In calculating in non-standard conditions, it won't be tested in how you think it is. I was just more or less letting you know what's coming in the next chapter, that you need to know more about equilibrium before you can apply it to delta G in non-standard conditions.
Okay.
I'm gonna write that down actually and just say if I can add to that for Sunday, just to provide more clarity and examples on Sunday's review. I'm gonna just write that down as a topic to talk more about. Thank you. I've got that note made. Cool. All right, friends, we're going to bring it to a close here today. Thank you for attending. I hope you found it valuable. I'm going to send the link out to all students, those who couldn't attend. So look for that in your email. I'll be back here Sunday at 2 for any last minute Q&A you might have. I'll prepare a few slides from things I noticed that were most missed questions from the quizzes. But please consider emailing me if you want something specific talked about. Stay safe, stay warm. Maybe I have to go shovel it again today, right? Thanks for coming, everyone. I'm going to stop recording and wait for everyone to leave.
Thank you so much.